Hello everyone, I am trying to do a video recording of me giving a lecture for Dr. Yang's test in case that we still have it on Thursday. I know that some tests have actually been canceled this week, but those were mostly Monday, Tuesday, and Wednesday, so I don't know if anything's going to be canceled for Thursday yet. I have not heard anything in case you were wondering. But I'm trying to do this review. I set up this video recorder, so I'm hoping that this all works out and you guys will be able to view it on Blackboard. So I don't have like a whiteboard here at my apartment, but I have this. I set this up to where my computer is really close and hopefully you can see everything that I'm doing. Today I'm just going to do an hour of chapter 14. And then I will move on to 15 tomorrow or sometime later tonight. So I'm doing this for an hour, so hopefully this will help you if you have any problems with chapter 14. So we're going to get right into it, and it should last only an hour. So hopefully you guys can watch this on your snowy day, and I hope you're being safe and everyone's enjoying some time off of school. Okay, so we're going to get right into it. You're mostly going to be seeing me writing on this the whole time, okay? So here we go. Let's start it off. Now, when we did so these are basically going to be on the workshops, and when we did these chapters, we first had, we're starting these chemical kinetics, and you guys have been seeing ice charts, right? So first, we have workshop 14, chemical kinetics, and we're going to go through all of these and should be able to within an hour. So here we go. Now, our first problem, if you want to, go ahead and take out your workshops, what you've worked on. I'll give you, about 20 seconds to get those out. That'll be a good reference for you while I'm going through this in case there were any questions that you had. And again, if you're going ahead and watching this video, I know we are not in the classroom currently, so you don't know, there's certain questions you may have that I don't address because I don't know what questions you have to ask, right? So if you watch the video and you want to go ahead and send me an email after you've seen it, you're more than welcome to if there's something that you don't quite understand after today. So it will be split up into 2 segments today, and hopefully this helps you guys since there's no sessions today or tomorrow. There's still, if classes resume tomorrow, there still will be Danielle's session, and the tutorial center is always open, but feel free to send me messages today. I will be home all day, obviously. So let's go ahead and get right into it. So we know, hopefully you all can see this. This is kind of hard, right? This was our first question. Sometimes the lighting has to adjust on this video. So it is asking us, I will read it in case you cannot, and hopefully you have it out in front of you. You study the rate of a reaction, measuring both the concentration of the reactant and the concentration of the product as a function of time, and obtain the following results. Which of the following chemical equation is consistent with the data? So we see this chart, if you can't see it very well, we have B doing something like this, and we have the other one. We have the other one going something like this, right? So we know from the reactions that we have done in class that reactants always disappear, right? So this is showing me that B is disappearing, and this is concentration, right? We see concentrations in brackets all the time. And this is time. So with time, this is depleting, right? Less and less concentration. So this is disappearing while A is appearing, right? And if you actually look at the chart on your workshop, you can see that this is almost double. So this is disappearing, but this is forming something double of the amount of that B is disappearing. So the answer ends up being D, because we know reactants always disappear, products always appear. So D states that B, just like a regular reaction where you show that an arrow is going to products, reactants form products, and it's about 2 times as much as B that's disappearing. So that's 2A. This is appearing, this is disappearing. These are my reactants. This is my reactant, this is my product. So hopefully that makes sense. Pretty self-explanatory. You just have to know that this is disappearing, this is appearing, so that's what's on the left side and that's what's on the right side. Okay, so I will have to flip through pages more often since I don't have as much space. Now, number 2, so this was number 1 on our worksheet. Number 2, Number 2 shows, for the following gas phase reaction, indicate how the rate of disappearance of each reactant is related to the rate of appearance. So anytime I see rate of disappearance or rate of appearance, I'm going to think of this delta concentration over delta T. Right? So every time I see rate of appearance or disappearance, rate of disappearance is talking about the reactants disappearing to form products. Rate of appearance will always be referring to the products. So now this is our reaction. N2 gas plus 3H2 gas is forming, I'm going to run out of room, 2NH3. So hopefully you have this in front of you so you can see it. Sorry, I ran out, but that's, ammonia at the end. 2NH3, right? So that's what it's forming, and that's also a gas. Everything's in gas phase. So if I just need to simply write the relationship between these, I'm going to say first thing you need to know, all reactants are going to be negative in this form. All products will always be positive because one's disappearing, one's appearing, right? So I'm going to say delta N2, and if we can write this whole reaction as 1. Everything equals each other. Now, there is only a coefficient of 1 out front of here, right? So that's always 1 over 1. You always put 1 over whatever you have here. So normally we just leave that as nothing, right? We don't put anything there. But since it's a reactant, it's negative. That equals, I have another reactant, automatically going to say that's negative. And there's a 3, so I'm going to say 1/3. It's always 1 over whatever stoichiometric coefficient you have out front. So now that's delta H2 all over delta T. And now, since we have a product, we're going to leave this positive, and you don't have to write a positive. You can if you want to, but you don't have to write a positive. You can just say delta. Now, there's a 2 out front here, right? Sorry, my products are down here. Forgive me any messy notes because of what I have to write on is not a whiteboard. Anyway, now we have 2 of these, so I say 1/2, and it's positive because it's a product. NH3 end bracket, hopefully not writing permanent marker on my wall, over delta T. So that's how you write up this whole relationship. This particular problem says indicate the rate of disappearance of each reactant and how it's related to the appearance. So what they ended up doing is they said just each of these separately. I'm sure that you could write it like this and it would be correct, everything related to each other. But what they formally wanted you to show the rate of disappearance separately. So this, how it equals to this. And then this, how it equals to this. So how they have it on the answer key, let's move on to the next page. Give me a second. I have some tape here to put it up. So what they wanted was everything separate. And again, I don't think it would be incorrect if you wrote the equation all the same. So what you could have said, I'll write this again, because now it'll be much neater. So if I just wanted to put them separately, again, and it said each of the reactants, rate of disappearance in regards to the rate of appearance of this. So this would be that's how that reactant reacts with this product. Now, if I wanted the other reactant, so see how I'm doing it separately? You can ask Dr. Yang, but I honestly don't think it matters if you put it all in one line like I had previously shown you, because that's still showing how each of them relates to one another. Right? So, negative, positive. Okay, so now that's how you write those relations with rate of disappearance or rate of appearance, okay? Now, the next problem is a little bit more complicated. I should probably put up another sheet of paper. A lot of people have questions on this, so I really want to show you what you do and you don't have to do. So here, the following data were measured for the rate of, so this is that one with the chart, right? It says the following data were measured for the rate of disappearance of NO in the reaction to NO plus O2. And this has all gas phase, you know, normally you keep that in there, but I'm just showing you what you guys need to use. So now we have this reaction and they give me a chart. So hopefully you guys can see this chart because I really don't want to write it all up here. So here is the chart. Yeah, I think you guys can see that okay. Now what we need to do for each experiment, and I'll show you how this works, we need to find where NO, if we want to find it says write the rate law, right? So if we're trying to write the rate law, we need to find where this is similar, the same number, and where this number is different. Say we want to find the superscript, of oxygen. We want to find where oxygen is different and where nitrous oxide is the same. So what I mean by that, what is a rate law? We haven't even written a rate law out yet, correct? So a rate law for this reaction, it is saying we do not know its superscripts. That's what it's assuming by giving us this chart. This rate law would be written K, rate times that constant, equals my reactants. So I need the concentration of both my reactants. When they give me a chart like that, it's telling me I don't know what these superscripts are. But rate laws will always be based on the reactants. So you never write products in rate laws. Other type of things you will be seeing soon, you will write like products over reactants. When you're writing a rate law, it's just based on, the rate is based on your reactants. Right? So here we go. Oh, and we do not know, by giving us this chart, it's saying we do not definitively know what A and B are. If they don't give you a chart, then you should assume that these coefficients out front are A and B. But by giving us this chart, we have to calculate for it. It says determine the rate law, so I need to calculate for it. Now again, what I don't know are A and B. So I go back to this chart. Sorry, it has to vary in the different amount of light. So I go back to this chart. Now where are my rates different? So if I look at NO, I can see right here that, oops, sorry, I'm trying to look at it and do this at the same time. I notice that NO is the same for 2 and 3, but oxygen is different. Oxygen is different for 2 and 3, right? So if I keep these the same, I'm finding that coefficient, that superscript, I'm finding that superscript for oxygen. So notice, again, oxygen has different numbers, nitrogen has the same numbers. We're looking at experiment 2 and 3. Okay? So let me put that down and show you what I'm talking about. So I said rate 2 and 3. We are going to write out an expression. Rate 2, rate 3. That means if I use those numbers for experiment 2, NO, for experiment 2, I look at the chart and I see my number, my concentration is this 0.252. A, I don't know what A is. I'm assuming I don't because I have this chart. Oxygen is this 0.0125. B. Now, if I look at my numbers for experiment 3, let's write in experiment 3. I have a rate of the same thing. And I want to have the same thing, and I'll show you in a second why. Now, oxygen has a different number. Right? So what does that mean? That means that I can cancel out, these K's can cancel out, These are exactly the same number with the same superscript. Now I'm looking at this. The only thing I'm looking at is what was different for oxygen. So I'm finding B in essence. Okay? So what does that exactly mean? That means I can set the rates. So let's look at this again. This chart again. And I'm trying to make it straight. I'm sorry for the confusion. Now we need to use these initial rates right here for 2 and 3. And we need to be able to relate them together, right? Because I said rate over rate. And it tells me what my initial rates are. So my rate for 2 is this. My rate for 3, initial rate in the chart, is 1.13 times 10 to the negative 1. And that equals these two divided by each other. Right? So this is initial rate 2 divided by initial rate 3. And this is what we just found up here by writing this rate law right there. So we divide by them to see what factor they're multiplied by. So if I divide this number by this number, it should be 0.5. This is 0.5 right here. This divided by this. And that is equal to 0.5b. Now, I notice in her worksheet, now that I'm looking at it, that she uses x and y. If you want to use a and b, sometimes I use m and n. Either way is fine. X and y, a and b, whatever works for you. We're literally just trying to find these superscripts, right? So that means my b is equal to what? 1, right? Because anything to the 1 will be itself. Anything to the 0 would be 1, right? So that is how you find the superscripts. Now I can do the whole exact same step again, but for NO. And now in my chart, I need to find where NO is different, but oxygen stays the same. Because if we set it up like this, then oxygen will cancel out, and I will find the factor that's multiplied by for nitrous oxide. I hope that makes sense. I know I'm not there to answer questions, but try to go through this, work with friends if you need to. This is how you set it up. Now, I've also been asked the question, well, do I need to write this out every single time if I can just look at the chart and realize where they're different? Then I can just divide by where the numbers are different. So what I mean by that, people ask me that question, is obviously we see that in this example here, that nitrous oxide cancels out. Do I need to really write that every time? No. You can get to this step and be completely fine. I showed you everything in case you're utterly confused about how to get there. Yes, this is the full way to do it out. If you can write this and you understand that things cancel out properly, 100% fine to write this out. Literally just from this step on is what you need to do if you understand that. This was just an understanding process, just showing you where it comes from, okay? So doing that, I'm not going to do the other one because I want to have an hour for everything. But doing that, we got B is equal to 1 and A is equal to 2. So try to do the other one on your own. Try to do the other one on your own to where you can see how to get this 2 value. But it's exactly the same way. Now, so our rate law, now that we know our superscripts, our rate can now be written as rate is equal to K NO squared. Sorry, it is really hard to write like this, okay? So I'm just putting that A right here and that B right here, or X and Y, or M and N, however you have used that before. So I hope that makes sense. I'm giving you, I know in class it takes a couple extra seconds from when I write it for you to write it. Okay, and then if you don't understand anything, you can just hopefully rewind, right? Okay, So now we've gotten, that's a pretty hard question, but I think it's fairly easy to follow once you know what to cross out. You're trying to find the difference to figure out its factor, okay? Now, this one's a good question. It states, what are the units for the rate constant? Do I have to, questions I get all the time, do I have to memorize my units? No. Here's a beautiful trick that teachers don't normally tell you. Your units are always going to be, I just figured this out with some students I worked with, n minus 1 s to the negative 1. So your units are always going to be s to the negative 1, but your m, your molarity, will change. And what I mean by n is your overall order. So if you memorize this, n is your overall order. So here, what's my overall order? 2 plus 1, right? So if I just say m, so 3, so 2 plus 1 is 3. 3 minus 1 is m to the negative 2, s to the negative 1. It will always be s to the negative 1, okay? But your m, she might put on a test, what is my overall order, or what is my units for an overall order of 6? And then you would know that it would literally be 6 minus 1 would be the answer. Well, it'd be 6 minus 1, so m to the negative 5, s to the negative 1 would be your units. Here the units are, again, just to reiterate, it's the overall order is n. So maybe I should write that. Overall order. Okay? So that's how you get that here. So hopefully that'll help you in case she tries to throw a trick like a multiple choice question at you or something, okay? So what is the average value of the rate constant calculated for the 3 data sets? So we can do that as well. What is the average value? So this is literally taking everything, plugging it in, and then averaging them out. So we know that our rate is equal to K, NO, was it 2? I was just looking at it. So NO2, 1, yes. So NO2, O2, 1. So now I look back at that chart. This chart gives me every concentration I'll need for each experiment, and it gives me every rate. So it's trying to find the average value of K. So you plug in every rate. So for experiment 1, I'll do one example, and then I'm not going to do all the averaging because you guys should know how to average by now. So that means from the chart, so we can reference the chart, my rate is 1.41 times 10 to the negative 2 is equal to K, which concentration of NO in experiment 1 is just this 0.126 squared, and then oxygen for experiment 1, 0.01251. Sorry, that's a little small for you guys to see, but hopefully you can visualize that, right? So now that I plugged in everything but K. So I, multiply. Oh, there's that one. So I multiply all of these together, right? And then I can take whatever I got here and divide and just get K. So we find out, that's pretty simple math as well. We find out here that for trial 1, my K is right? So here we have this, here we have this. Now we need to do it for experiment 2, we need to do it for experiment 3, right? And whatever my K values are for each of these, I take all of them, add them together. So K for experiment 1 plus K for experiment 2 plus K for experiment 3, all divided by 3. And it says, what is my average value for the rate constant? So we know K is rate constant. Okay? So you find the average value, and my K-Av here is 71. So it's always they're always going to be very close to one another. Oh, shoot, I wrote down the wrong one. So K-Av, that was for a different one, sorry. 7109.26 is your average. That was just an example. So when I found all of these different Ks, added them together, divided by 3. Okay, so that's pretty easy, just plugging in each experiment separately. All right? Now we will move on to, oh, the next part is part of this as well. Sorry, I just smacked the computer screen. Okay, so the next part of this, it says, what is the rate of disappearance of NO when the concentration, when we have one concentration of NO and we have another concentration of O2. So, let me put up another piece of paper. Now, rate of disappearance and rate of appearance. What did I say at the beginning of this? That's when I have those delta values. Anytime I see rate of reaction, rate of appearance, rate of disappearance. Now I have regular paper because I ran out of blank paper. Okay, so here in this case, what is the rate of disappearance? So this is what's given. Given is NO concentration 0.0750 molarity, and O2 is 0.01. Okay? So this is what's given to us in the problem. It's asking for what is the rate of disappearance of nitrous oxide when we have these concentrations. That's the first part of the question. The second part of the question says what is the rate of disappearance of O2 at these concentrations. So this is given to me first. Rate of disappearance, I know, is this, right? And normally a reactant is negative, but we don't have to worry about that here because our rates will never, that's only when we're showing a relationship between two, right? So we'll see that in the next step because we're trying to show a relationship between this and O2. So, okay, we're going to say this and rate. This is equal to the rate, which is also equal to what we just found. Okay? So, we know all of those are equal to one another, right? So we have rate of disappearance equals a rate, which is also equal to the rate law, right? That's a rate law that we just found in part A of this same exact question. So this is D. Now, what we do here is we literally plug in what they gave us. So to find this rate of disappearance, which is this right here, I say rate. I say this is equal to what I just found for K in the previous problem. So what is my K? My K is what I found in part C. So if you have your paper in front of you, you can see that you have part C. Part C is what gives me K. And remember, it was this 7,000 number that we found. And I'm not writing the units, right? The units are m to the -2, s to the -1. You probably will for the test, but I just don't want to run out of room writing this, okay? So now they give me these concentrations, and anything in brackets are concentrations, right? So I write 750 squared, and then my O2 was given to me as well, 0.0100, also to the 1. Right, so hopefully you guys can see that. I think it looks decent for me, but I have fairly good eyes and don't wear glasses. Okay, so that's how I'm going to set that up, and that's the rate of disappearance once I multiply this whole thing out. So my rate is literally going to equal, for NO, nitrous oxide, sorry, that point's a little far away, 0.3997 molarity per second. So remember, when we were talking about units previously, when it was n-1 and all of that, when we were talking about units, it meant units for the rate constant. So don't be, rate is different. Rate should be molarity per second, but rate constant will change. So don't get those two confused, as a side note. Anyway, so now we have our rate of disappearance for NO. So you could say like rate NO, rate of NO, fine, whatever makes you more comfortable. Now we have to do a relationship type question because we are trying to say rate of disappearance versus rate of disappearance of nitrous oxide, NO, versus rate of disappearance of O2. So that relation, if we write it out how we had previously, so rate of disappearance of O2 over delta T, it should have concentration. I'm seeing this answer. Key does not, but it should have those concentrations around it. I don't think that they'd count off if you forgot them, but it should technically have this. And remember, from the previous pages, that's what stinks about having to do it on this computer. Previous pages, we know that the actual equation is, let me write it down again. So this was on page 1 of your workshop. 2NO plus O2 equals 2NO2, right? So that means when I'm writing this relation, this should just be 1 over 1, right? Because that coefficient. Now this should be negative 1 over 2, because now we're looking at the relationship between these two because they gave me something for NO in the problem. They said find the rate of disappearance of NO. So I found the rate of disappearance of NO, but it should be different because of these coefficients out front, right? So now I have delta of NO all over delta T. So that's my relationship between the two. So the thing to note here is that when I plug in these values, so these negatives end up canceling each other out, right? So it should all stay positive. Your rates should always be positive. It should work out to where they should always be positive. Now, if I plug this in to find my rate of disappearance of O2, it should be about half as much as NO's was, because NO has 2 times more, right? So I hope you all can hear me well. I don't know how good this program is for recording lectures. So now I plug in this negative 1/2, and again, these negatives go away because they're both on the same side. But anyway, 1/2, and what was the value I got previously? 3,997 M. So that's, when I'm writing a relation, I have to take into account those negative values. Otherwise, we should know that our rates should always be positive. Okay? So here we are. That is our answer for that. I'll give you a couple more seconds to write that down if you are watching and writing at the same time. Okay? So I hope that makes sense to everybody. Practice these over and over again. That's my biggest advice. If you want something else to do besides, I got this question recently, if you want something else to do besides just doing these workshops, go through her lectures. I do not think personally that going through the book word for word is the smartest way to study. I'd go through her lectures and these workshops and know how to do them forward and back. Because she likes to stick things from her lecture in there, you know, especially if someone didn't show up one day, like a lot of people didn't show up one day for a lecture, she will use something from her lecture that she stated in class. So if there's something you don't understand from that too, make sure to ask your TAs and everything. Okay, so now moving on. The next question, the decomposition of sulfuryl chloride is a first-order process. The rate constant for decomposition at 660 K is this. So they give me a rate, and they give me a temperature in this first part, number 4. So this is our compound. It's a first-order process. So this is just what's first order. So these are all important parts. My temperature is 660 K, and I have a rate of 4.5 times 10 to the negative 2 inverse seconds. Okay, so all of this will be important for our problem. Now, part A. If we begin with initial sulfuryl chloride pressure of 450 torr, what is the pressure of this substance after 60 seconds? So, this part A, gives me a pressure of 450 torr, right? And then what is the pressure of the substance? And they give me a time. Time is normally a small t, so big T is normally temperature. Time is normally small t, and that is 60 seconds. Now, there will be equations on your test that will be given to you for first order integrated rate law. So we know, more likely than not, when we're given a time, we know that we're going to be using, and they tell us it's first order because that's when it really matters. They're telling me it's first order. They're giving me a time. I'm probably going to use an integrated rate law. Now, these things, I'm pretty sure you don't have to memorize, but you need to know. You need to know what they look like in order to use them properly, right? So for a first order process, my integrated rate law, and I should be able to recognize this. And this is for pressure. Now, for any of these problems, if they give you a pressure over a concentration, like let's go back to this problem here, another thing to consider. Okay, let it straighten up a little bit. Okay, so you see this chart that I gave you, or that was given to you? If these were all instead of concentrations, because we see the brackets, correct? I see the brackets here, but if I was given pressures and it said P of NO, which it would be a big P, and NO would be as a subscript. If I was given a pressure, all of this stuff would be exactly the same, okay? So it's not going to be any different. So just think, concentration and pressure, they're fairly interchangeable, okay? So just use it as if it was a concentration if it's given as a pressure. I hope that makes sense because it confuses a lot of people. So now, the decomposition of this is a first order process. So I know first order processes look like this. KT plus ln of PO. Again, this can be, you've probably seen this as AT in brackets, right? You've probably seen it like this. It's exactly the same thing. You use the equation exactly the same way. She's starting to throw pressures at you because she wants to, she wants to know that these things are interchangeable. These equations are interchangeable with concentration and pressure, okay? So now I'm looking at this, and I see, you need to know exactly what these mean. This is a pressure at a specific time. This is a pressure initial. Anytime you see that knot, sometimes you see something like this, a knot up here. Anytime you see those like knots, sometimes it means pure substance, which you guys have seen before, and a lot of times it means initial. Those things mean initial. That zero, it looks like a zero, or a lot of times people call it knot, means initial. So this is my initial pressure. This is my pressure at a specific time. Now, if I was using these, again, that would mean a concentration at a specific time, and this is initial concentration before anything has happened. Initial, okay? So you need to know what those means. Again, this is our rate constant. That is a specific time, and we know that ln's are, math functions, right? So now I just have to plug in. The question asks for, if we begin with an initial pressure, ding, 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 I need to use initial. Initial pressure of this, so pressure initial. That's what we can say right there, right? P initial. We begin with the pressure of this. What is the pressure of the substance after 60 seconds? Right? So what is the pressure after 60 seconds? That's what I don't know. I don't know what the pressure is at a specific time. I only know the pressure at initial. I only know initial pressure, right? So they give me a rate, 4.5 times 10 to the negative 2. They give me 60 seconds. It should always be in seconds, so if it's not in seconds, if it's minutes, you need to convert. Then we say plus ln of my initial pressure, P naught, 450 torr. And yes, your pressure can be in torr. And millimeters mercury and torr are the exact same things, right? So that's what we're going to always use, millimeter mercury and torr for them, because they equal the same thing. So if she gives you 450 millimeter mercury, it's exactly the same thing as 450 torr. So don't get tripped up by that, all right? Now, so once we've done all of that, so we type in this plus ln. So we know how to type ln into our computers, right? Our computers, ln into calculators. So we get ln of PT is equal to 3.41. How do I get rid of ln? Hopefully some of you are talking to your computer right now and it is telling you that you put it to the E, right? So to get PT by itself, to get rid of ln, you say E to the 3.41. So as long as we do that, hopefully you can see that, you can get rid of your ln's, okay? So now I have about 20 more minutes until I'm done. So I'm going to skip over the next one. At what time will the pressure, so the question is, at what time will the pressure decline to 1/10 of its initial value? The only thing I'm going to say, and I want you to solve it on your own and get the answer in the that you got on the worksheet. Sorry, you can hear me with my tape, trying to tape up more piece of paper. Right? So the only thing I'll tell you about part 4B is the fact that it says, at what time will the pressure of this sulfuryl chloride decline to 1/10 of its initial value? So you're trying to find time here, so you're leaving time blank. And what you're saying is that your PT is equal to 1/10 of your initial. And then for the initial, you're just leaving initial is equal to initial. So you're leaving those two together, and let's see what it says on the other page. You're leaving those. That's what you plug in basically, so you can get rid of that variable, right? So try to follow. It's actually very well written. Danielle wrote this workshop. So it's very well written and very easy to understand her math from her workshop. And then your T should be 51 seconds. So try to follow that one on your own. The biggest trick is that you need to put in this PT, this pressure at a specific time, as 1/10 of PO. So this is what you'll be plugging in, both of these, into the equation. So follow her math. It's very good. It makes a lot of sense, okay? So we're moving on to number 5. A certain first order reaction has a rate constant. These are actually my favorite ones because they're very easy and you should not mess this up. Number 5 is an activation energy question. These are all very simple. A certain first order reaction has a rate constant, so hopefully we can fit it all on this. Number 5, first order has a rate, so rate constant, also equal to that K, lowercase k. I always write it as cursive, so it's obvious it's lowercase, but you can just keep it as a lowercase k. 2.75 times 10 to the negative 2, okay? And it's at 20 degrees Celsius. So this rate constant, rate 1 and T1, these two are related to each other, so I'm going to write them as K1, T1. What is the value of K at 60 degrees Celsius if the activation energy is 75.5 kilojoules per mole? So now I'm trying to find K2, no idea, at a time 2 of 60 degrees Celsius. Right? So now, at 60 degrees Celsius versus the 20 degrees Celsius, and we have an activation energy, EA, of 75.5 kilojoules per mole. Now this one's pretty easy. We have an equation that will be given to you. You just have to know to use it, which should be pretty obvious because it's the only one that should have EA in it. So, K1 over K2 equals EA over gas constant time 2 minus time 1. So basically, all you need to know is what to plug in where. I labeled it very nicely because I knew exactly what this problem was asking for. So I said K1, and this is the time or the temperature related to K1. K2, this is the temperature related to K2. I'm looking for when it turns to this temperature. So I'm going to put this temperature in here, Kelvin. Remember, I have to add 273 to this. So it's 60 plus 273 fits right here. 20 plus 273 fits right here. EA, obviously, is what they gave me here. R is my gas constant, right? So that gas constant may or may not be given to you. Probably will be. But just in case, 8.314 is joules per mole K is what you'll be using here. Okay, so now for this one, I have everything that can plug in, and all I need to find is K2. So K1 is right here. So if I have all these values, now that you guys have seen the setup, let me just plug it in real quick, and it should be fairly easy how to get the answer, okay? There are a couple little tricks, and that's why I'm actually going through the math of this. Alright, so everyone wrote down hopefully what I just wrote, or you can follow just fine. So if ln K1, K2 is equal to, now on the previous page I wrote that my activation energy was 75.5 kilojoules per mole. My gas constant is in joules per mole K. So I need to transfer this one to joules. This is joules per mole, right? So joules per mole, pretty obvious. Just remember that because this is joules per mole K, we need to have everything in the correct units. So I put that there, and then I put my temperatures in. And my temperatures are, and now I don't have room, right? But the temperature should be right here, right? T2 minus T1. And my temperatures, again, will be 1 over 333. So that's what's going up here. I'll write an arrow. And 293 K. Okay? Here. So that's what goes there. And then we get to the value, ln K1 over K2 is equal to 3.72293. All right? And now this is fairly simple. We have this ratio, and all we need to do, once we have this ratio, what should I do next? Should I try to figure out, like, you know, how to divide these two, how to make this work? Because we do have a value for K1, correct? We're just trying to find K2. No, what I do, get rid of that ln. Put this thing to the e, right? Say K1 over K2 is equal to e of negative 3.72293. Yep, get rid of that. So then, once I have this value, which is K1 over K2 is equal to 0.024163. Now, once I have that, fairly simple, right? All I need to do is plug in that K1 value, which is that 2.75. So here I can say 2.75 times 10 to the negative 2 inverse second. Sorry, that almost looks like a 3, but that is a 2 to the negative 2. So this is K2, right? We can say this over, once we do the math to get K2 by itself, right? I'm obviously getting K2 by itself. Divided by, K2 divided by that value, oops, that value right there, 0.024163. So I'm basically just getting K2 by itself. I'm plugging in for K1, which is not what we did here, but it's much easier to get rid of that ln as soon as you can, okay? So hopefully that makes sense, and you get 1.14 inverse second, right? Okay, hopefully that helps. Now we are going to the last few problems, which are actually much easier than these previous ones, right? So now we will move on to number 6. And again, if you have questions, hopefully you can ask your friends. I'm trying to do this as a courtesy to you guys since I was not able to on Monday. And then you can sit and watch this in the comfort of your home, not worrying about going to school to do this. So hopefully this helps you guys, and if you really like it, I'll think about doing it again. You just let me know. I would love to hear your feedback on what you all think. So if you get a chance, write me an email and let me know what you think, okay? Great. Now, number 6. What is the molecularity of each of the following elementary reactions? Write the rate law for each. So these are very easy. So part A was 1. It was Cl2 to 2Cl. Now, this one's very simple because it says write the rate law for each. So honestly, what do we do for rate laws? We only worry about the reactants. So rate is equal to K Cl2. Right, and they don't give us a chart. Remember, they gave us a chart for that problem on the first page, so I needed to find out what these coefficients were, right? If they don't give me a chart, it's understood that these coefficients out front apply. So that'll just be to the 1. You don't you never actually really write the 1, but if you do, I don't think they would count off either. But you shouldn't write the 1. So try not to write the 1 if it's, just like they don't write it here, you don't have to write it there. Okay, so we understand that's 1. Now, what is the molecularity? When they're talking about molecularity, they're talking about the unimolecular or the bimolecular. There's only one reactant here, unimolecular. Okay, fairly simple. I'm sure you guys already understand this. So for part B, it has a longer equation, and I'm not going to write it up here, but it is bimolecular because it has a rate that depends on 2 reactants. So let me throw it up here. I'm sure you guys have already seen it. So you see that part B? It has 2, in the rate it has 2 reactants, and both of them have a stoichiometric coefficient of 1 out in front. That OCl minus has a 1 out in front, and that H2O has a 1. So it is a bimolecular process because it has 2 that it's basing the reaction off of, okay? Great. So I didn't have to write that one out because these are really simple. Okay, now number 7, our last one for today. The following mechanism has been proposed for the gas phase reaction of H2 with ICl. Part A. Write a balanced equation for the overall reaction. So this should be pretty easy. I should be able to fit this all on here. Number 7. All I have to do for this one, it says write a balanced equation for the overall reaction. I add them together. That's all I do. H2 plus ICl plus HI. And these are all in the gas, so I did not write it because I'm doing this for simplicity. Now we have, these are 2 reactions that are both given here. ICl I2 plus hydrochloric acid. Everything's in the gas phase. It says write a balanced equation for the overall reaction. I'm going to add these two together, and anything that's the same on both sides gets canceled. All the reactants on one side, all the products on the other side. So it's going to be H2 plus ICl plus ICl plus HI yields HI plus HCl plus HCl plus I2. So now anything that's the same I can add together. So I can say 2 ICLs, 2 HCl's. Now what's the same on both sides? What's the same on both sides? HI. So that gets canceled from my overall final reaction of this, okay? So it'll be H2 plus 2 ICl, 2 HCl plus I2. That's my overall reaction. Makes sense, pretty easy. And make sure when you're writing these, I'm not doing it, but you guys have to make sure you write gas with everything, and they may count off, okay? So, identify, part B is identify any intermediates in the mechanism. Intermediates, what are intermediates? What did I cross out that were the same on both sides? That's my intermediate. There could be one, there could be more than one. So, intermediate is that HI that got crossed out on both sides. Okay? Fairly simple. And our very last problem for today, yay. If the first step is slow and the second one is fast, which rate law do you expect to be observed for the overall reaction? So, super easy. It's telling me this first reaction that was given right here is the slow one. The slow one, as you've probably heard, is the rate determining step. So if they're telling me this is slow, this is fast, I'm going to use this one to write my rate law. Make sense? It should. It's pretty easy. So that first one is my slow one. I am going to base my rate law out after that very first mechanism. So what we're going to do, I'm sure you guys already know how to do this because this one's super easy. That means I'm just going to write the answer. Rate are the reactants and their coefficients, which just should be 1, which you don't need to write. But that is the very first reaction that they gave you. So this reaction right here, so they have this times that, both their coefficients out front are 1. So my rate law is simply this, and that's it. So it's based on the slow. So the slow is commonly called the rate determining step. Okay guys, well that is it for today. So I really hope this helps, and I really hope this goes through, because I have been trying to figure out since yesterday how I could do this for you guys. So I hope it's really helpful, and you can write me amazing reviews for at the end of the year that I was a really good head TA, because I'm really trying. And if you have any questions based on this video, there's still some things that you don't understand since I wasn't there to answer, please just email me. If you don't get a hold of me, you should. But if you don't get a hold of me for some reason, email your TA. I'm sure they'll be good with answering your questions as well. So I hope you guys have a wonderful rest of your day off, and good luck on Thursday. And if we still have the test, but hopefully this will get you to where you need to be. All right, guys, well, have a good rest of the day.